Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at bipartite graphs. So they are just graphs or networks that contain no cycles or only even cycles. So in this network here, this would not be a bipartite graph. We have a 3-cycle here. This is an odd cycle because it's a cycle involving 3 vertices. On the other hand, this here is a bipartite graph. The only cycle has 4 vertices, so that's what we call an even cycle. So with bipartite graphs, you can split them up into 2 sets of non-adjacent vertices. So here, I could split them up into a set that's A, D, and E, because these vertices are not connected by a single edge. And of course, the other set will be B, C, and F. They are not connected either. So A is adjacent to B and C, D is adjacent to B and F, and E is adjacent to B and F also. So these are what bipartite graphs look like. They're very useful for problems in which you have 2 sets. Let's look at one of those now. So here I have a bipartite graph. It's clearly bipartite because A doesn't connect directly to B, B is not adjacent to C, and similarly for D, E, and F. So we have what we call a weighted graph where each edge has a weight. Now in this example, A, B, and C represent processes or servers, and D, E, and F represent tasks. Bipartite graphs are great for these sort of assignment problems. I'm going to assign to each processor a task. These numbers represent times taken. What I want to do is assign the tasks to the processes in such a way that it reduces the overall time taken. So this is an example of the assignment problem. And to solve that, we use the Hungarian algorithm. It's complicated and all the steps are here. We will go through that. First, what we have to do is set up a matrix. So this is like an adjacency matrix, but instead of writing how many edges, say, connect A and D, we're going to write the weight of the edge that connects A and D. So from A to D, the weight there is 10. So we put a 10 there. And the weight from A to E is 19, and so on. So we're going to perform the Hungarian algorithm, i.e. these steps, on this matrix here. This will lead to an optimal assignment. So the first step is to perform row reduction and then column reduction by subtracting the smallest element in each row or column. So first thing I'm going to do is row reduction. I am going to take the smallest element in each row and subtract it from every element in that row. So in the first row, I subtract 8 from everything. I get 2, 11, and 0. In the second, I subtract 7 from everything. And in the third, I subtract 6 from everything. Now I'm going to do the same with columns. So in the first column, I'm going to subtract 2 from each of the elements. Then I'm going to subtract 11 from each element. And the third, I subtract 0. It goes like this. All right, the thing is, whenever we get a 0 in the matrix, it represents an optimal assignment. We need to make sure that the number of independent zeros sort of stacks up. So we do that by doing step 2. We want to cover the zeros with as few horizontal and vertical lines possible. So I can cover the zeros with 1, 2, 3 lines. So here I am done because the number of lines I used is 3, and 3 is the number of rows, also the number of columns of the matrix. So now we're going to draw a reduced bipartite graph. See here in the A row, it says that I can assign A to any of the 3 tasks. But I don't want to assign B or C to the first task, which is D, because I didn't get a 0 in that column. So the optimal allocation, A is going to be assigned to task D. Now, for B and C, it's not clear from this which way I should assign them. I could assign B to task E or B to task F. It actually doesn't matter here. I can either get 24 if I assign B to E and C to F. I'll also get 24 if I assign C to E and C to F. So either way, it doesn't matter in this particular example. So I'll just choose E and F like that. So A to D, that took 10 units of time. B to E takes 18, and C to F takes 6. Overall, the optimal allocation, it will take 34 units of time to complete the task. Now, if I had a situation where the number of lines that I drew to cover the zeros was not 3, was not the same as the number of rows, I'd have to do a few more steps. They're very simple to do, but they're just a bit time consuming. That occurs when you don't get enough zeros, where it's not clear from there how you should assign the tasks. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.